Okay, so thanks for the invitation. So first of all, I'd like to have a disclaimer that I'm myself not an algebraic geometer. And in fact, I started formalizing things because I learned algebraic geometry and was not satisfied with like the arguments inside. So I started doing these kind of stuff. Okay, so let's probably first talk about what algebraic geometry is. So algebraic geometry is the study of polynomial equations, or more specifically, zeros of polynomial equations. And we study the geometry of it using algebraic methods and stuff. Or on the other side, if you are more in algebra, oops, what happened? Algebra person like me, this is also another way to view like abstract commutative algebra in a geometric setting. Like we can view the prime ideals as points, we can view the abstract elements in a ring as functions, and etc. Yeah. So this field has a long tradition, but there's a modern reformulation based on Grothendieck's EGA, which is very nice written. It is both abstract and rigorous, but then on the other hand, really based on like concrete examples and concrete motivations, and is really suitable for formalization. So like formalization geometry is in part easier because of his seminal and other French school seminal work. And also there are other very nice sources about like rigorous treating of algebraic geometry, such as a Stack's project. And also Rary Vakil has a book called The Rising Sea, which also has some nice insights and intuition that's not found in other sources. What is the elements of algebraic geometry? Yep. Okay, so this is a brief history of how AG started and AG is developed in Mathlib. And so everything started in early 2018 when Lean is still in Lean 3 and it's relatively new and there's almost no library on it. And Kevin Buzzer and a bunch of students, undergrads at Imperial, did the first formulation of schemes, which is the central object of algebraic geometry. And then I joined in mid-2021 when schemes hit Mathlib. And then we got gluing and fiber products. This is quite a nice milestone because gluing, if you don't know what scheme is, imagine like topological spaces. We have two things and we have a thing that's isomorphic. I want to identify them together and make a big topological space. This thing is really easy in conventional math because we can easily glue things in our mind, but this is really not the things that proof assistants are meant to be doing. Excuse me?
Wasn't it an axiom in the scheme?
Not really. Like, it's an axiom that scheme looks locally like affine spaces, but if you have some two thing which are locally affine spaces, you want to kind of patch them together. It's construct like the space and the functions on it and etc. Like, or I mean, it depends on what your definition of schemes are, but basically, like, this is not that easy to do, and it's quite like to show that Mathlib or algebraic geometry or the definition scheme can really handle these kind of geometric operations and stuff. Yeah, so that's 2022. And then there's a year when things stopped for the big port from Lean 3 to Lean 4. And after that, we got variative criteria, which is also a nice milestone. And in 2024, we got a quite nice refactor, which stemmed from some conversations in a workshop. And I will talk about some outcomes of that later. And finally now, where we finally got projective spaces and italicites, these are by other contributors. And on yesterday, the PR that projective spaces are proper or complete is finally merged. So yeah, it's still very much happening and things are being developed right now. So, but did you notice something strange here? Because look, the things are moving so fast here, but there's a 3-year gap before schemes were introduced, but and these schemes went in Mathlib. Like the queue is long, but it's not 3 years long. So there's some story behind this. But before we delve in, we need to start talking about what schemes are. So loosely speaking, for every commutative ring, we can attach a scheme to that. And it's if our commutative ring looks like this thing, then the scheme is just the zeros of these polynomials. And then we also, aside from the space of zeros, we need to consider the data of the functions on the schemes. Here's a quick reason why we need to consider them. Because we're dealing with equations. And for example, the equation x equals 0 and the equation x squared equals 0 are different equations. And they sometimes have different roots. For example, in this ring, c of x quotient x squared, there's this non-trivial solution of x squared equals 0, but there is no a non-trivial solution for x equals 0. So there are different objects, and we will forget this if we only consider the roots of it in our base field, for example, c in this case, because like the roots are all x equals 0. But we don't want to forget the data of maybe one has some other roots when you do a field extension. So basically, you retain this data by looking at also the data of the ring of rational functions on it. And here I said that the zeros form a topological space, but this topology is not the standard one. It's the one generated by sets like D of F, where F is for all F in R, where F in R, which is a polynomial ring. So this is a polynomial, and this is the set of X such that F of X is non-zero. And from this, you can kind of see it's either a theorem or by definition, depending on your definition, that the rational functions on the zeros of F all look like are localized at F, which means F to the something over another function. Like, because you guarantee F is non-zero here, you can divide by F. And some theorem tells you that F is the only thing that you can divide by. So anyways, this is the data of an affine scheme, which is a space with a topology generated by these things. And then another, for each open set, you have a ring of rational functions, where on DF it looks like this. And these are affine schemes. And schemes, on the other hand, are ring space, which are abstract topological spaces with rings of rational functions attached to it. And it needs to satisfy some axioms like the sheaf axiom. But anyways, a scheme is a ring space that locally looks like affine space schemes like this. So if you're more familiar with, say, differential geometry, this is modeling like manifolds, where manifold is an abstract topological space where locally it looks like Euclidean spaces. Okay, so this is schemes. And so, as I said, the story started in 2017, 2018, where they started to do schemes, but there are no algebra library in Mathlib yet. So they just did everything by hand. So they build this topological space, they write out what the functions are, they prove that the functions are the right thing, and they try to jam them together into a big space called a scheme. But this turned out to be very painful and very hard to work with. And so they redid this with an is-localization API. So as I said, this rational functions on D of F is the localization of R, but we can't say this on paper or mathematically, but actually you mean that this is either isomorphic to the localization of F, or by localization, you mean some predicate, some universal property that's unique, up to some isomorphism. So I wasn't there, so it's they. They started by actually writing down like fractions and stuff. I realized that's not the way to go, and changed to an universal property thing, which is the is-localization API we have in Mathlib now. and that's the second try. And then, but this is still not satisfactory, so they try the third time, and this time using some category theory. As I said, the ring of functions, rational functions form a sheaf, and this is some general thing and some category theory nonsense. And they use that category theory nonsense developed by Kim Morrison, I believe, to do all this. And it turns out to be really nice and way easier to work with. And this is the definition we ended up in Mathlib. And as I said, I wasn't part of the process, but this story is very nice and well documented in this paper by 6 authors. Like 2 authors on first try, 2 authors on second try, and 1 on third try or something. And they wrote a paper together, which is this one. Okay, so that's the third try. And now I propose the fourth try, which is, do we really care about sections on non-affine opens? Like, I've talked about schemes and stuff, but I've never told you what the sections look like outside of these DFs, because they're not really well behaved and look really ugly. So this is the definition I propose, which is we don't consider the sheaf on the whole topological space. We consider a distinguished basis and then a sheaf on the basis. And some like comparison lemma of sites tells you that this corresponds to what we already have. And for schemes, you similarly don't consider all opens, but you consider a dense of sites, which is some weaker version of bases, topological bases, and you consider the sheaf on it that locally looks like an affine scheme, and locally means the usual locally thing. And these are the objects in our category. And what are the arrows? Usually we have like morphisms of sheaves, but this doesn't work because usually we have a scheme X to Y, oops. And we have a sheaf here, and then we say that we map OY to X the push forward of OX. But under this definition, there is no push forward because like the key thing is the pullback of like the preimage of an open set is open, but the preimage of an affine open is not necessarily affine open. So if we only define things on affine opens, this will not work. But then you can just talk about all pairs of affine opens such that the image is contained in another, and then a map from one to the other, satisfying the usual assumptions, and that they locally look good. Okay, but before I move on, I like to add a disclaimer that people do care about sections of other affine opens. So I was lying there, but I'd rather argue that sections on non-affine opens are like things calculated from the scheme and not essentially part of the scheme. Like here, the canonical example is H0, which is the global sections of the scheme. But I argue like, when you specify a scheme, you don't specify the H1s. Why should you specify the H0? They shouldn't be part of the data. Okay, so this is the fourth try I'm proposing. But does this mean that I'm redoing all algebraic geometry? Does this mean I'm scrapping the definition of Mathlib or like extending the 3-year war on schemes to 10 years? No, definitely not. But I like to interlude and make a point about formalizing definitions in math or in Lean. So there's this community wisdom that definitions are the hardest and the most important, and it's very important to choose the right definitions. But I claim that this is not the most important thing. And my argument is that maybe a not so good definition it needs some more API and some more effort to make it usable. But after you do the API, then the difference is not noticeable and it's not important. For example, maybe you know adjunctions in category theory. There there's two definitions, right? There's one where the Helm sets correspond, and there's the other where you talk about units and co-units. And which one is the better definition? I don't know, maybe there is one. But which one is the Mathlib definition? I don't need to know because there are API for both of them, and there are API for interacting them in both points of views. So it's not important which one it is. So what I'm proposing is not to replace the schemes, but to add API support to this point of view. But wait, one would argue that this extra effort is ugly, and I thought mathematics is all about aesthetics. And yes, you are right. So maybe we should change that, but that will only come after we actually make sure that this definition is better, which I don't think it is. I just think that it's better in some ways. And to back this up, I had an experiment, which is formalizing ideal sheaves. So the usual definition of ideal sheaves is an ideal sheaf is a quasi-covariant OX submodule of OX. You don't need to know what all of them means. You just need to know that quasi-covariant is a notion on sheaves that is also it can be defined on ring spaces because Mathlib, so that's what we did. But the consequence of that is that the API is not usable at all, and it's quite some work to connect that to the ground and to actually work with them how we usually think about them. So what I did is I defined an ideal sheaf to be an assignment of each affine open U to an ideal of OX of U. So here I only care about the sections on affine opens, and then you need to satisfy some compatible condition. And in lean, it looks like this thing. So on a scheme, you have for every affine open, you have an ideal of the section and satisfying some compatibility condition. So using this stuff, we are able to show that ideal sheaves correspond to closed subschemes of a scheme. And this is not straightforward even with a good enough quasi-covariant API. So let me talk a little bit about the proof. So the proof is that for every, as I said, I had a sheaf that takes a U to a common ring. Oops. I should erase some of these. I take U to a common ring OX of U, and then I have an ideal. So I can form the quotient ring, a quotient thing, which is U maps to the OX of U, quotient I of U. And then this thing magically is associated to some scheme. And to check that, you need to check that this is locally an affine thing. So you need to still restrict to the affine things, and then check that they are isomorphic to the right affine schemes. So in the end, you still need to restrict to the affines to do this proof. And so why don't you just start with affine sections and just do that? So what's next? Okay. So and earlier this morning while I was playing with oh, by the way, this equivalence was merged also yesterday. So I was playing with it in Mathlib this morning, and I even realized that you can get the functoriality on ideal sheaves without knowing what the sections on non-affine things work. As I said earlier, like the issue of this is the pullback of an affine open is not necessarily an affine open. So it's not immediately clear what it means to pull back an ideal. But I found out there's a nice way to do it without even mentioning like non-affine sections. So I would say that this is quite a successful experiment, and this point of view is actually quite nice and is useful in formalization stuff. Yeah. So this is the story about schemes. And I like to move on to talk about local properties. This is the outcome of the massive refactor that I talked about. And so the main issue is, as I said, schemes. What are schemes? Schemes are things that locally look like affine schemes. So because that's the definition, so it's not hard to imagine that all proofs start with, for example, this is Hartshorn. You replace y with an affine neighborhood y, and so so you can assume that y is affine. But this kind of makes no sense. There are two ways you can interpret this. There's one way where you have an scheme and you have a affine open, whatever that means, and then you have a point here. And then we take U to be an open subset of X, and then Y is, if y is in U, then Y is automatically an element in U. But now what does it mean for this to be affine? This cannot simultaneously be a subset of X and also be a spectrum of an R. So there's an isomorphism here that he's hiding, and we need to deal with it in lean, and this is very painful. And the other approach is to not talk about open subsets. We talk about like abstract open embeddings, open immersions. But in this case, it's not trivial that a point in X is automatically a point in this string space. And there's some pullbacks things that you need to do, and he's also hiding that. So, and this is another example from Stacks, which says that, oh, you choose an affine neighborhood and the dimensions are equal, and then we reduce the affine case and we're done. But the dimensions are equal, fine, because they're like topological constructs. But the other objects in the statements are like residue fields and stocks of our scheme, and it's not immediately clear how to pull back that into an affine open neighborhood, and how these isomorphisms are compatible and what's not. So he's also hiding something. And then this final example from Ravi Vakil's the rising sea, which should be quite rigorous, which also is. This is rigorous, but it just omits a lot of details that we do. Like in paper, we just say that we do quick reductions. We shrink Y, we shrink X. Yay, we're done. Everything is fine. But that's not how lean works. That's not how formalization works, unfortunately, for now. Hopefully things will change. But yeah, the question is, how do we do this in lean? So here's an definition. A predicate P on a scheme is local if X satisfies P, if and only if an open cover that satisfies things. So basically you can check things on an affine and on an open cover. So you can reduce things to affine opens and deal with that. So you can have statements like this. And this is pseudocode because I've not implemented this in Mathlib, but this is possible, which is we have predicate, we somehow say that it's local by this definition, and then we should be able to get an induction principle, which says that if P is satisfied by all things like spec R, then P is satisfied by all X. And then we're done, are we? Unfortunately, we're not. Here's a typical example of another argument in algebraic geometry. And the proof is, because this is local, you reduce to algebra and you're done, yay. But what does it mean for that to be local? What does it mean to restrict? So here's the picture. I have a morphism F from X to Y. And then you have an open set here, the names and this thing, and you want to restrict F to this. And this is what it means to restrict. So you need to restrict both on X and Y. So you cannot directly apply this induction hypothesis. I mean, you can interpret this as a statement like for all morphisms on that affine implies separated, but you still need to restrict this thing, and you need to do that by hand if you don't have a good machinery to deal with it. Yeah. So the solution we come up with is a predicate on morphisms, which says that if a predicate is local at the target, which is y, if and only if for every open cover of y, p restricts to u holds, then p holds for the original morphism. Yeah. So if you turn this into lean, it looks like this, which is exactly what I said for all morphism and all open cover of y, then p of f is only if p restrict of f. And this respects iso thing is a notion that almost never comes up in paper math, but this is very useful here. And the statement is that p of f, if and only if p of e composed with f for all, for all isomorphism E. This doesn't come up in mathematics because like a sensible mathematician won't write a property that doesn't respect isomorphism. Like we reason things up to isomorphisms, and maybe the univalence people have a better solution to this. I really doubt so, but maybe they do. But our solution in lean is to consider morphisms, morphism properties that satisfies this thing, and also on the other side, and carry this hypothesis around so that we can disregard isomorphisms in certain circumstances. Yeah. So talking about this morphism property, here's a quick interlude. Morphism properties is also something that we don't talk about explicitly in conventional math because they're just so trivial. They're just predicates on morphisms. But we've also managed to develop an API over these adjectives so that we can like formally manipulate these adjectives and do proofs like this. This is quite nice. I can show you this, and where is it? So here's a proof. So let me change this to light. Okay. So the statement is proper equals evaluative criterion holds and it's quasi-compact, quasi-separated, and locally of finite type. And to prove this, I just rewrite with is proper X, which says that this adjective is equal to the conjunction of all these. And then I rewrite with this, which is that is separated is the conjunction of these two adjectives. And then I just rewrite these step by step, and then some automation could just finish up the thing. Oops. So it's a quite nice API. And at the start, I only use this for scheme stuff for this other geometry, but other people like Joe Ryu also started using this for some property, and their localization of categories API is also based on some of these things. Based on might not be accurate. I should say they used some of these things. Okay, so this is a quick interlude. It's quite a nice thing. Like this proof looks very cute and I really like it. Okay, so where were we? We were at local property of morphisms. So here, this is local at target. And by the name, you can guess that we also need local at source too, which is this thing. Like now we consider instead an open cover of X. And then we say that F restricts to all UI holds if and only if F holds. And turned into lean, this is this thing, which looks almost identical, except this X, Y is turned to X, and this restriction is slightly different. Yeah. And the issue about this restriction being different is also the reason why we need two different predicates, because we will need to know how to restrict the morphism on the target and on the source, and there are genuinely different operations. So with this and the other thing, we can define this might not be important, but we can define has affine property, which says that some morphism property is local, and we have a nice description of them on affine opens. And then we are able to package lots of locality arguments nicely. For example, compact. For example, this is the file defining the predicate of being quasi. So all this is like the proof of it being local. And here we get to the statement that, that quasi-compact is local, and it's given on affine opens by the property of being a compact space. And after that, we can just use our has affine property API to get all these nice things that it says is stable under composition, is stable under base change, and etc. And this really makes these locality argument easier, but for more complex things other than this like boilerplate stuff, you still need things like how do I find any? Is this a nice example? Yeah, you need to like rewrite things with is local at target, and you try to massage things into the right form. And so, for example, this is a proof that, oh, this is not a good example because the proof is sorry, but maybe go to ideal sheaf. Oops. Oh, this is an example. So the proof, the statement is that the support of the kernel is the closure of the range, whatever. Like, but the proof is, first of all, we reduce y to affine. I should make this bigger. And then a big boilerplate of how to reduce this. And then we log that the source is affine, and then a big boilerplate of how to do this. And then the actual proof is just this. So comparing what's like trivial on paper and what's the actual content of the proof, you can see that this is really not good, and we really want some good solution to this. Yeah. So are we done? No, we're not. Like examples, maybe we have 3 schemes, then maybe we want things about this diagram, which we often consider because of pullbacks. And then we need 3 predicates. We need locality on this, locality on this, and locality on this. And maybe we want a different diagram that looks like this. And we need this locality on this, locality on this, and locality on this. And that's 6. That's 6 predicates. And maybe we want 4 schemes, and then we have a bunch of different diagrams. And maybe 37 schemes, and I don't know what we do. And here we only deal with schemes, but as I said, we have affine stuff, ideal sheaf, we have like stocks, we have sections, we have bundles, how to restrict them. Everything restricts differently. And how do we have a uniform way of doing all of this? So back to the question, how do we do this in Lean? And the answer is, I don't know. Yeah, but at least we now have a large amount of formalized AG that we can experiment on, try to have some maybe a unified way of expressing what to be local, and a unified way of expressing what to restrict a thing means. And then maybe we can try some automation on the existing proof. Like there are lots of different proofs like this, and maybe we can go over each of them and see what things are involved in that. And for each thing, where in the proof are we restricting that thing? Where in the proof are we showing that that thing is local? And try to somehow modularize this thing. Yeah. Or maybe on the other side, maybe this is just an constant overhead and this is just something that we need to bear with. We need to just maybe because we've been developing algebraic geometry for quite some time now, and this problem was always there and it doesn't really get better or get worse. So maybe it won't get worse as we go along and we just deal with it. But on the other hand, we are just at the most surface level of algebraic geometry. So maybe we haven't done enough things to find out if it's actually true or not. So yeah, we'll need to see. But this is the dim future. But I shouldn't end here, so I should talk about some of the exciting future, which is we have all these basic notions, we have all these basic tools. We are now actually in a place where we can start talking about actual geometry and actually doing some cool stuff with it. So here are some projects that are either ongoing or haven't started, but are possible. First of all, torus gravities, this is one that's started about 2 months or so. And so maybe if some people have been to the London Learning, you have heard of them talking about this stuff. Basically, there are two sides of torus gravities. There's like the combinatoric side and there's the algebraic geometry side. And you can find some correspondence between them. And if we have a good API, they're sort of like the testing ground of theories of algebraic geometry. And on the other side are maybe group schemes, which also are present in torus gravities and perhaps elliptic curves. Elliptic curves are the most basic object in perhaps arithmetic geometry. And we do have some of elliptic curves in Mathlib, but let's look at the definition. Elliptic curve or curve. It even lives in the algebraic geometry library folder, but oops, this is my secret stuff. Which is a fine maybe, or I should just go here. Yeah, the definition is a tuple of 5 numbers, which represents a curve, a equation, and this is yeah. And oh, and the numbering is A1 to A6, which 5 is missing because of some concerns. But yeah, basically, this is our definition of Weierstrass curve. And we really want to link this to this vast algebraic geometry API we have and try to both generalize the arguments there and specialize our approach into these settings. And we're very close in doing this, but we're still missing some stuff. Yeah, so there's that. And on the group scheme things, we are able to show that group schemes over algebraically closed fields are smooth and some other nice properties about it. So it's very possible to do stuff about group schemes now, but we just need to do them. And here's another thing that I'm working on, which is EGA 4.6 or 4.8, which is limits of schemes and stuff. And after this, we can talk about like adelic points, and we can maybe try to state some local global principles and stuff, maybe. But this EGA 4.8 is very technical and very painful, and it deals with like diagrams of co-filter stuff and try to glue things to get limits. Yeah. And another thing that is almost within reach is a form of Zariski main, which is not the full thing. The full thing needs cohomology, but there's a proof in Qing Liu, which uses substantially less stuff to prove a slightly weaker result. And we are in the place of working on this too. And finally, sheaf cohomology. Like the main thing of algebraic geometry in Mathlib for the past 3 years is how much we can do without sheaf cohomology. But we're almost out of things that we can do. So maybe it's time that we actually think about how to do shape homology. Ryu has a great API about homology that's recently that's almost mature and we are almost able to use it. But to actually calculate stuff, we need to link that to some more concrete calculations that also needs work. Some people in Utrecht in the Netherlands are thinking about this. Yeah. So these are the future projects that might be fun to work with. And if people are interested, feel free to contact me and we can try to tackle on some of these stuff. Yeah. And that's about it. It's about early, but yeah, that's my talk.
Yeah, so I remember at one point in your code, you like I saw an at stack tag. Like so, I was wondering whether your formalization somehow like you have you're sort of like mapping theorems that you formalized in the with lemmas from the stacks for you, sort of making it.
Yeah, there's yeah, but this is nothing more than a tag, and it's like multiple to multiple relation, and it's just not. It's probably nice to search for stacks tags. It's easier if you have a stacks open and you need to search for a particular thing and such. Yeah, and maybe later there will be a way to make this into a database and such. But for now, it's just a tag.
Maybe like you were talking, saying that like one of the hard things is dealing with local properties
Yep.
and restrictions, and I was wondering if like analysis people would be facing kind of the same issue. You know? So to me, like analysis feel also a lot about like restricting to neighborhoods. But I don't know like how much this is might be different context facing different problem.
I think they work over a big ambient space. So their restriction are all restriction into subsets, which like there are lots of predicates of like an analytic on subset and stuff and how to restrict them onto points and onto neighborhoods and stuff. But I'm not aware if they have like different things where they have abstract spaces and they need to restrict. And yeah, I'm not entirely sure.
So you think that your setup is harder to deal with because it's more like modulo isomorphisms.
Yeah,
You are like
I mean, for the manifold people, they have charts and when proving things, they need to try to like prove things on the Euclidean space and pull back to the chart and show that they're compatible in somehow. And maybe this is similar to what we do, but on the other hand, the manifold library is also very immature, and I think they haven't decided on what the best approach to these kind of argument is as well. Yeah.